Hello and welcome to this lecture on parallel imaging. Slides contributed by myself and Dr. Jeremy Gordon. And this covers MRI, the basics, chapter 24. So here's going to be the goals, learning goals for this chapter. We're going to go through what are the key requirements to perform parallel imaging, what is the concept behind these so-called sense methods, how are the so-called GRAPPA methods different from sense, how does parallel imaging change the SNR, what artifacts can appear in parallel imaging, and what are the benefits of parallel imaging? Okay, so back to the fundamental concept of MRI is that it's compared to a lot of other imaging modalities such as like ultrasound or CT. It's a rather slow imaging technique, and really one of the main limitations is the speed or the temporal resolution. And if we can speed up the scans, we can get more scan coverage of larger volumes. And like diffusion imaging, we can get more B values. We can capture dynamic information like heart motion or contrast agent kinetics, and ultimately keep the subject in the scanner for less period of time too. So what are the different options or different ways we have for acceleration? Well, we've talked about a few of these. There's so-called multi-shot approaches where we have echoplanar imaging or EPI or fast spin echo, where we require multiple phase and loading coding lines per excitation pulse. We can actually reduce the phase encoding steps, although the resolution suffers. You think of any other ideas? And the title of this lecture is going to be one of those other ideas. So let's do a brief review of our data sampling requirements. And here's our full field of view, full resolution image, where we're covering the entire 2D case space. And well, one way we could think of accelerating would be to just throw away. So these dotted lines represent lines that we're not acquiring in 2D case space, but of course, as you know now, this is going to give us worse spatial resolution in the direction of this restricted sampling. So that's not good. The other option for throwing out phase encoding lines is to increase the spacing between the phase encoding lines. And now we do actually maintain the spatial resolution, but our field of view takes a hit. With a smaller field of view, and like in this example, this can lead to aliasing. Okay, so how can we reconcile this? How can we keep this big KY max, which gives us our spatial resolution, but cutting down on our number of phase encodes? And so this is the idea of parallel imaging. And the concept here is that we're going to use our array of receivers, our antenna, our receive RF coil, and they actually provide some additional localization beyond what's in the magnetic field gradients. And this is what's going to allow us for acceleration of imaging with sub-Nyquist sampling. This technique has been around for almost 20 years or so now, and it's very standard and become a workhorse of modern MRI scanners. And we'll unpack a couple of these pictures here on the right in the remainder of the lecture. So let's review what receive coil sensitivity means. So we might have our transmit coil, a volume or sometimes called body coil, that has this large homogeneous sensitivity profile. That means it creates the same magnetic field over a large volume. But our receiver coils are most sensitive right near the loops of wire. So this example here of this 4-element array loop. And then being shown at the far right is the bright red, indicating where each of these four individual coils is the most sensitive, so where it's going to be receiving the most signal from, and then that drops off as we get further away from the RF coils. And here's another way of looking at that, of sort of a simplified example of, say, on the head, we had a coil on one side and on the other side, and one of the coil will give us an image of basically half the head, and the other coil will give us an image of the other half of the head. A couple good rules of thumb to keep in mind here. The depth of the RF sensitivity profile is approximately equal to the diameter of the coil. So we can look at these individual coil maps or images that you see here, and we can kind of estimate, well, actually what about the size of these individual coil elements was. Okay, and so a normal workflow up to this point we would have considered, but we've got our distribution of our net magnetization here at the left. Okay, then it's gets multiplied by this sensitivity profile. So this is some weighting that's placed on top of the image. And each of the receiver coils gives us a different image. In this case, 8 different images from each of the individual receiver elements. And we do the so-called sum of squares combination, the equation given here. And what happens is, even though these individual coils, their sensitivity may drop off, together they're going to cover the entire image with better signal actually than our larger volume type coils. So it's advantageous from a signal to noise point of view to use these local RF coils. Now, how can we do parallel imaging with this additional information? So we want to sample data below the Nyquist requirement, which normally leads to aliasing, but we're going to use the spatial encoding information that's actually captured in the RF coils to fill in our missing case-based data. And there's 2 major classes of techniques for parallel imaging. The first is so-called sense methods. This problem is fixed in image space. Can we use the explicit coil sensitivity profiles to try and measure or approximate these sensitivity profiles? And then there's sort of another popular approach, commonly called GRAPPA, where we're actually going to perform the reconstruction of filling in these missing data in case-space, and we're going to use the data itself to estimate the coil sensitivity, or more accurately, the coil correlations, to fill in the missing data. Okay, and we'll go through both of these techniques here. Okay, so we want to dig in here is what we might do is this type of sampling pattern here, where again we're going to maintain our full extent, our full maximum sampling in case-space, but we're going to try to do some acceleration. And as you can see, which direction we're going to accelerate in, we're going to do it in the frequency and phase encode. Well, it doesn't really make sense to pull out points in the frequency encode because that's a continuously sampled dimension. So we're going to do our undersampling in the phase encoding dimension. And then there's actually a very important concept related to the coil geometry I'm going to show here. And that is we need some explicit coil information in the direction we want to accelerate here. So in this picture, if we have these 4 RF coils stacked next to each other, we need to accelerate in the direction where we have differences between our RF coils. So in the left to right direction in this picture, these RF coils look the same, but in the up-down direction in this picture, the coils obviously look very different because they see very different portions of the image or the subject in the sort of up-down direction. Okay, and then if we expand a little bit on how the sense method works, think of it this way: is we start off with our object, in this case somebody's head, and remember our object is transverse magnetization, and we might have a certain signal intensity IA and IB at 2 locations. And what we're going to get in our individual coil images is the multiplication of these intensities, or these transverse magnetizations at these locations, A and B, multiplied by the coil sensitivity profile, in this case denoted C, at these same 2 positions, and basically get this shaded image that you see at the far right. Now, what happens when we undersample the data is that these 2 voxels, and as it's drawn, A and B, will overlap. Okay, and that's what's being shown in the picture here, is that now instead of having the separate blue and red voxels, they actually, when we have the field of view, these blue and these red voxels, or the A and B voxels, overlap onto each other in these 4 images represent the 4 different RF coil images. And so what you can see in the math here is that we have the signal intensities that we want to recover I at both of these locations, multiplied by the coil sensitivity profile for coil 1 at the top, coil 2 below, coil 3 below that, and coil 4. And what you can start to see from this is now we have an equation here where we have these F's are 4 measured values. We have our 4 measurements. We have 2 unknown values, IA and IB. And what the sense method says is, well, if we can measure, or we can somehow know these C, the coil sensitivity profiles, then we can simply solve this system, this linear system of equations, to solve back for our I for our unaliased image, okay, illustrated in the bottom right here. And so the key requirement for the sense methods, so we can, again, we're going to skipping these lines in K-space to create this aliasing, is that we need to know the coil sensitivity maps. This is often done from some low resolution images where we divide by the body coil image to account for any differences in magnetization amplitude. And the sense method is very powerful, very common. It has a couple pitfalls. The most significant of those is if we have inaccurate coil sensitivity profile measurements. So if we don't know these C for the individual coils, then that leads to errors in the reconstruction. Okay. And that's what both of these are saying, either inaccurate measurements or imperfections in these measurements. And then, for example, if there's require separate calibration in real scan, and you have motion occurring between either the coils or the subjects, then we're going to see errors. And they'll typically look something like this. So what is being shown here is these are residual aliasing artifacts. So the signal here is originating from out here in the skull, and similarly on this side. It's originating from some other location, but we're unable to remove. So we have the aliased images. We're trying to go back to this unaliased images here, but let me erase this so you can see the artifacts again. We're unable to remove some of these residual aliasing artifacts, again, due to one of the reasons listed at the left here. So the other major technique, GRAPPA, aims to address some of these limitations of sense. And GRAPPA is a K-space approach. So we're going to need to look at K-space. And it uses the model that is shown in the figure at the right, where we have our image and the K-space data along the bottom. And when we multiply our image by the coil sensitivity, we obviously get an image that looks like just this region of the anatomy. But in K-space, this is a convolution with the Fourier transform of the coil sensitivity profile in the bottom middle portion here. And so it's like the smearing of information across K-space to neighboring points. And so what we would do is, for GRAPPA, is you basically undersample like normal, like you showed before with skip phase encoding lines, except we need to acquire a few extra lines in the center, which are commonly referred to the auto-calibrating region or the auto-calibrating signal. And this is at fully sampled but coarse spatial resolution. And so what we can do from this auto-calibration signal is we can estimate basically what's contained in that blurring kernel from the individual coil sensitivities to say, well, what is this how is this information being smeared across neighboring K-space points? And if we could estimate how it's being smeared, then we can use that to fill in our missing data. Okay, so let's go through a comparison here between the sense and the GRAPPA methods. In regard to sense, it's going to use a sampling pattern like the one shown at the right, where it's going to require measurements of the coil sensitivity profiles. It's going to do this in image space. It's called sense on Phillips Siemens, acid on GE. And it's a little faster than GRAPPA because it does not require the auto calibration signal, but more sensitive to motion and the calibration step. Whereas GRAPPA, which is a class of auto calibrating methods, then simply estimate the coil sensitivity or coil calibrations from our fully sampled center of K-space. GRAPPA on Siemens, ARC on GE, a little more robust and performs better in low SNR regimes, but it also has a slightly less maximum acceleration achievable. And overall, they're both used and both perform relatively similar. Okay, another key concept in parallel imaging is, well, what happens to SNR? And there's a new part of our SNR equation that we're going to need to add here due to the fact that the reconstruction can be poorly conditioned. And what does this mean? We're trying to use the coil geometry to separate as an additional spatial encoding piece, but if the coils are not configured in the right places or the right locations, or we don't do the undersampling correctly, then there's not enough information in the RF coils to do the reconstruction problem. And so we characterize this, so this poor conditioning actually leads to increased noise in certain imaging regions, and ultimately limits how much parallel imaging acceleration we can perform. And so for parallel imaging, we have this modified SNR equation, where part of it is related to the undersampling factor, which I often abbreviate as R. And this is actually coming from our standard SNR equation, that if we go R times faster, since SNR depends on the total square root of the total measurement time, then we're going to have a square root of R less SNR just due to measurement time effects, just do we sample for less time. But we have one other term here, and that's a so-called G factor penalty. And this captures how good or how bad our coil geometry, spatial location, undersampling pattern, acceleration factor are. How good a job can they do in supporting the parallel imaging reconstruction problem? So let's dig into this G factor a little bit more. It's the G factor is a numerical measure of how difficult it is to solve whatever parallel imaging equations. Sensor GRAPPA, it should always be greater than or equal to 1. We don't get any sort of gain. And highly dependent on the coil geometry. It's going to be worse if the coils are highly overlapped on each other or have very correlated sensitivity profiles. And it's going to get worse at higher acceleration factors. So here's an example from the MRI from Picture to Proton book showing different acceleration factors of 1.5, 2, 3, and 4. So that means we're going 1.5, 2 times, 3 times, or 4 times faster. And we see the G factor map here gets worse. And you can see this in the unwrapped or the reconstructed images. At the bottom is that as these G factor gets worse and worse, then we start to see residual aliasing artifacts, and we'll also see noise amplification. And so here's an example of the noise amplification in a brain example, where an acceleration factor of 2, it's not very noticeable, but acceleration factor of 3, It's more noisy just in the center of the brain here. And that's because the center is seen similarly by all probably the RF coils on the outside. So it's harder to, there's less independent spatial encoding in that center region. And then this just gets worse at the R equals 4 acceleration factor, which also shows some residual aliasing artifact that was not removed by the reconstruction. And finally, it's actually dependent on the sampling pattern used as well. So here's a simulation of a G factor for two different case-space trajectories. One are simple, just skipping lines in case-space. And at the right, we see that it actually has a worse G factor penalty, where you get these very bright red. This is going to be bad regions. These are going to create more significant noise amplification, whereas this concentric rings trajectory, which is basically sampling case-space on these circles, is actually going to have a much more favorable G factor penalty. And the basic intuition is that the sampling pattern is matched to the RF coil sort of layout in this case. Okay, and now we've looked at this just for examples in 2D, but turns out so we can extend this into three-dimensional scanning. So what are we going to need to do in this case? We're going to need to consider, well, now we have basically two phase encoding dimensions, and in the example we're showing here, there's a quote one phase and a quote-unquote partition dimension as well. Okay, and in this example, the coil variations are in Y and Z, so here, or the phase. So the Y phase, and the X is the partition. And note that what I said here is that, again, we have coil variations only in Y and Z, so actually not in the X direction. So between the two part A's here, difference is one is doing the acceleration in the proper direction, in the phase. This one is trying to do acceleration in the direction in the left to right, which in this example, there's no coil variation as stated at the left. Therefore, this leads to a very high G factor, very noisy images. And this is for this sampling pattern A shown at the top here. So I've just answered that question. And then the next question is looking at the bottom. We can do acceleration, do the sampling patterns B and C, where we do some acceleration in both dimensions, okay, and do this kind of almost looks like a checkerboard or 2 dimensions, I guess, of undersampling here. And so we see this performs pretty well, although we are still trying to do acceleration in the partition dimension, so we do see still some residual G factor penalty or aliasing. And there's a little bit of a subtle difference in how the sampling pattern is shifted between B and C, leading to this delta 1 penalty, and gives this slight improvement in the parallel imaging reconstruction performance. Okay, and one other technique we've talked about recently is echoplanar imaging. So how would we use parallel imaging with echoplanar imaging? And that can be illustrated with the diagram shown here in the right. So here's the sequence diagram. where the gray indicates without parallel imaging and the blue indicates with parallel imaging. And so what we see is we're doing the zigzag in k-space, but we're jumping sort of 2 grid lines every phase encoding step, where we have slightly larger phase encoding blips compared to the gray sequence. And this allows us to actually, you can see, shorten the echo time, reduce the total readout length, or in other words, increase the bandwidth in the phase encoding direction. And so this is going to lead to a couple of different benefits. One is actually, recall, if we would just simply reduce the readout duration, this reduces our displacement and distortion artifacts due to off resonance or chemical shift. And so you can see in the examples at the bottom, the brain shape as we go to higher acceleration factors actually looks more accurate, particularly in the front sinus region of this brain. And that's because we're shortening the readout duration, and also there's reduced T2 star blurring simply because we have both a reduced echo time, so actually less T2 star waiting, and then if the readout is shorter, there's less time for T2 decay to occur as we traverse k-space. And I'll leave this as an open question for you to think about, and maybe something we can discuss in class. Is sense or GRAPPA better suited for an EPI pulse sequence? And here's another example of the reduced, with a parallel imaging factor of 2, we have a more realistic, or more accurate, not just realistic, more accurate shape of the brain anatomy here down in this relatively lower region where we have a lot of susceptibility that changes the magnetic field, and this leads to these displacement distortion artifacts with EPI. Okay, so to summarize, parallel imaging, now routinely used to accelerate MRI acquisitions, and the scan time reductions it provide can be used in a number of ways. They can shorten the total acquisition time, improve spatial resolution, temporal resolution, or simply overall image quality. And we just have a few requirements, is that we need to have a phase array receive coil, so it has multiple receive elements. It needs to do undersampling, and we need to match the undersampling with the direction of the elements in the phased array coil. And we need to start off with some high SNR so that when we shorten the acquisition and lose SNR that way, and maybe we lose a little SNR due to the G factor penalty, that we still have enough SNR in our images. And we talked about these two sort of main approaches. There are sort of variations within these methods, as well as other ones that we'll not talk about here. But these cover a lot of the major concepts used. We have the sensor image-based methods, that we need the knowledge of the coil sensitivity profile to perform the unaliasing and reconstruction. And then we have case-based methods like GRAPPA, where they use some auto-calibration signals and to generate or learn a convolution kernel. And this will perform reconstruction of missing lines in k-space. And remember that we have both a scan time reduction penalty and G factor penalty in the SNR. And the G factor penalty in particular leads to this spatially varying noise amplification that can be quite obvious, and it depends on basically our imaging setup as well as our case-based sampling pattern. Okay, here are a few other resources you might find helpful. And again, our goals for this material on parallel imaging. Great, thank you for watching.